Sometime around 1840, a machinist named Otis Tufts was walking through Boston when he came across a construction crew building the new custom house. These men were doing something that human beings had been doing for thousands of years. They were lifting a heavy iron weight, hauling it up on ropes, and dropping it onto the top of a wooden pole to hammer it into the earth, over and over again. The men were drenched in sweat, their arms shaking, the progress agonizingly slow. One timber driven a few inches at a time, all day long, in the Massachusetts heat. Tufts watched them for a while. Then he went home and came back the next day with a set of drawings for a machine that would use steam pressure to do what those men were doing with their bodies. That machine was the steam pile driver, and it changed the way America built everything from railroad trestles to skyscrapers. But the story of hammering long poles into the ground did not start with Otis Tufts. It started 5,000 years before he was born. On the banks of Loch Tay in Scotland, ancient builders were already driving wooden stakes into marshy lake beds to build their homes above the waterline. These were called crannogs, and they were some of the earliest permanent structures in Europe. The stakes held up wooden platforms that kept families safe from flooding, predators, and rival clans. The builders had no machines. They used rocks or heavy logs swung by hand to pound the stakes down into the mud. It was brutal, simple work. The stakes split sometimes, arms gave out, men slipped in the mud and went under. But the technique worked well enough that people kept doing it, passing it down through generations, for millennia. The Romans took the idea and ran with it. When they needed to build harbors, bridge piers, and military fortifications, they drove wooden piles into riverbeds and coastlines using small timber rigs and drop hammers. These were the first recognizable pile-driving rigs in history. A heavy weight, usually stone or iron, was lifted by ropes wound around a winch and then released to fall onto the head of the pile. Gravity did the work. Human muscles provided the power. And this basic concept, lifting a weight and dropping it onto a pole, remained virtually unchanged for over 1,000 years. But no place on Earth pushed pile driving further than Venice. The city that tourists know for its canals and gondolas is actually built on top of a hidden forest. When barbarian invasions started tearing through mainland Italy in the 5th and 6th centuries, refugees fled to the marshy islands of the Venetian lagoon. The mud and shallow water made it nearly impossible for armies to follow. The problem was that those same muddy islands were a terrible place to build anything permanent. The ground was too soft. Stone buildings would just sink. So the Venetians came up with an answer. They drove millions of wooden stakes, cut from the forests of northern Italy, Slovenia, Croatia, and Montenegro, deep into the lagoon floor until they hit a layer of hard clay beneath the silt. Then they laid platforms of stone on top of those stakes and built their churches, palaces, and piazzas on the platforms. The entire city of Venice sits on top of roughly 10 million timber piles. The Rialto Bridge alone rests on about 12,000 of them. And the Basilica della Salute, one of the most recognizable buildings on the Venice skyline, reportedly required over 1 million wooden stakes just for its foundation. Each stake was transported to Venice by water, floated down rivers and across the Adriatic from forests that were hundreds of miles away. The sheer volume of timber consumed by Venice's foundations contributed to the deforestation of entire regions in the Balkans, permanently altering landscapes that had been forested since the last ice age. And here is the part that still surprises engineers today. Those wooden piles, many of them more than 500 years old, are still holding the city up. The reason is chemistry. Wood rots because of fungi and bacteria, and both of those need oxygen to do their work. But the piles beneath Venice are buried in waterlogged, oxygen-poor mud. Without oxygen, the organisms that would normally break down the wood simply cannot survive. Instead of rotting, the wood slowly absorbs minerals from the surrounding water and sediment, and it hardens. Over centuries, those wooden piles essentially turned to stone. When the bell tower of St. Mark's collapsed in 1902, workers dug into the foundation expecting to find rotten wood. What they found were timber piles from the year 900 that were still in excellent condition, solid enough to support the rebuilt tower. So pile driving worked. It had worked since the Stone Age, but it had a ceiling, and that ceiling was human endurance. For most of history, driving a pile was one of the most physically demanding jobs in construction. The basic setup looked like this. A tall wooden frame, called a rig, held a heavy weight suspended by ropes. A team of workers would pull on the ropes, sometimes in a star pattern around the pile head, hauling the weight up as high as the rig allowed. Then they would release it. The weight would crash down onto the top of the pile and drive it a few inches deeper into the ground. Then they would haul the weight up again, and again, and again. In ancient China, workers used a stone block as the hammer and arranged themselves in a circle around the pile, pulling ropes in a rhythmic pattern to flip the stone up and guide it back down. It was coordinated, exhausting labor. Teams of 10 to 20 men might spend an entire day driving a single pile a few feet into the earth, depending on the soil. Soft riverbed mud was easier. Gravel or packed clay could slow the process to a crawl. Rocky ground could stop it entirely, snapping piles like matchsticks or blunting them until they refused to advance another inch. And the piles themselves were limited by what nature provided. Timber piles could only be as long and as wide as the trees they were cut from. In most cases, that meant piles topped out somewhere around 40 to 60 feet, with diameters rarely exceeding about 12 to 15 inches. Pile driving rigs grew more sophisticated over the centuries. By the 1400s, engineers like Francesco di Giorgio Martini were drawing up mechanically detailed designs for pile drivers, powered by gears, pulleys, and animal labor. Leonardo da Vinci sketched his own versions. In 1737, a London watchmaker named James Valloux built a horse-powered pile driver so effective that the Royal Society of London awarded him the Copley Medal for it. His machine was used in the construction of Westminster Bridge. But even the best animal-powered and human-powered rigs could only lift so much weight, so many times, so fast. A team of horses or oxen could drive maybe a dozen piles in a day under good conditions. In bad soil or with longer piles, progress slowed to a handful. For centuries, the fundamental problem stayed the same. To build something in water or on soft ground, you needed piles. To drive piles, you needed enormous amounts of repetitive force delivered over long periods. And the only source of that force was muscle. Then the steam engine arrived, and everything changed. In 1839, a Scottish engineer named James Nasmyth was working at his foundry near Manchester when he was asked to help solve a problem for the steamship Great Britain. The ship needed a massive paddle wheel shaft, about 30 inches in diameter, and no existing forge or hammer was big enough to shape that much metal. Nasmyth sketched a design for a new kind of hammer, one powered by steam pressure. A piston inside a cylinder would lift the heavy hammerhead, and then steam would be released, allowing the hammer to fall under its own weight. The design was brilliant in its simplicity, and it offered something no human-powered hammer could match: precise, repeatable, tireless force. Nasmyth patented his steam hammer in 1842. The Great Britain ended up switching to a screw propeller and never needed the paddle shaft. But Nasmyth's steam hammer became one of the defining tools of the Industrial Revolution. It could forge enormous pieces of iron and steel, and it could drive piles into the ground faster and deeper than any crew of men or horses ever could. A single steam pile driver could now do in an hour what used to take a full crew an entire day. Almost simultaneously, across the Atlantic, Otis Tufts was having his own moment at the Boston Custom House. He saw those workers struggling with manual pile driving and recognized the same opportunity Nasmyth had seen in metalworking. Steam could replace muscle. Tufts designed a steam-driven pile driver that used pressurized steam to lift the hammer for each blow, eliminating the need for ropes, pulleys, and human labor. His invention could drive piles deeper and faster than anything that had come before. And its timing was perfect, because America was about to embark on the largest construction boom in its history. The railroads were coming, and railroads needed bridges. By the 1860s, the Transcontinental Railroad was pushing westward across a continent full of rivers, valleys, ravines, and swamps. Every one of those obstacles needed a crossing, and the fastest, cheapest way to build a crossing was a timber trestle. A trestle is basically a series of frameworks, called bents, that hold up a deck of track. Each bent is made of angled timber piles driven into the ground and braced together. Building a trestle meant driving dozens, sometimes hundreds, of heavy timber piles into riverbeds, creek bottoms, and marshy ground, often in remote locations hundreds of miles from the nearest town. Everything had to be hauled in on supply wagons or on the rails themselves, right behind the grading crews who were cutting the roadbed through wilderness. The timbers were typically Douglas fir or southern yellow pine, and the longest ones stretched 40 to 60 feet, heavy enough that it took a team of men just to maneuver one into position under the rig. In 1863, the Central Pacific Railroad used a pile driver to build a bridge across the American River in California. That machine was in operation even before the official groundbreaking ceremony. Across the Sacramento River and through the soft swampland of the Central Valley, driven piles became the foundation of choice for bridges and trestle after trestle. The railroad shop buildings at Sacramento were themselves built on top of driven piles because the ground was too marshy to support stone foundations. The challenge was mobility. Railroad construction moved fast, sometimes miles in a single day, and the pile-driving crews had to keep up. Competitors like Industrial Works solved this by mounting steam-powered hammers onto railroad derrick cars. These machines could be towed by locomotive from one bridge site to the next. By 1885, self-propelled pile drivers were rolling down the tracks under their own power, reaching speeds up to 20 miles per hour. The hammer leads, the tall vertical frames that guided the pile and the hammer, stood about 45 feet high and could be raised from their transport position in about 30 seconds using engine power. These machines were essentially mobile construction factories, carrying everything they needed to drive piles on site. The hammers themselves came in two varieties. Drop hammers relied purely on gravity. The steam engine lifted the weight and then released it. These were simple, reliable, and required skilled operators to judge the drop height and timing. Steam hammers went a step further by using steam pressure not just to lift the weight, but also to accelerate it downward, delivering blows with far more force than gravity alone. The difference was substantial. A drop hammer was limited by how high you could lift the weight. A steam hammer could add downward force on top of gravity, hitting harder with each stroke. This mattered because American bridge builders were no longer just driving 40-foot timbers into shallow creek beds. They were tackling the largest rivers on the continent. In 1867, an engineer named James Buchanan Eads started construction on a bridge across the Mississippi River at St. Louis. This was not a timber trestle. This was a massive arch bridge made of steel, one of the first of its kind, and its piers needed to reach all the way down to solid bedrock beneath the Mississippi's deep, fast-moving channel. Eads had spent years as a salvage diver on the Mississippi. He knew the river's power to scour the bottom, shifting sand and mud with every flood. He decided that nothing short of bedrock would make a safe foundation. The problem was that bedrock lay more than 100 feet below the water's surface. To reach it, Eads used something called pneumatic caissons. These were enormous hollow boxes, built from thick oak beams and covered in iron plate. The Eastern Pier's caisson measured 82 feet by 60 feet. Workers would climb down into the caisson through an airlock, descend into a 9-foot-tall working chamber at the bottom, and dig out the riverbed by hand, while compressed air, pumped in from above, kept the water from flooding the chamber. The air pressure inside was immense, as high as 55 pounds per square inch in the deepest stages. The temperature was stifling. Candles burned brighter than usual in the pressurized atmosphere, and sounds were distorted, muffled in some spots and amplified in others. As the workers excavated soil and rock, masons above laid course after course of stone on top of the caisson, and the sheer weight of the growing pier slowly pushed the whole structure deeper into the river. It was ingenious. It was also killing people. The caisson started sinking in October of 1869. At first, nothing unusual happened. But as the chambers pushed past about 60 feet below the water's surface, workers started getting sick. They would finish a shift in the pressurized chamber, climb back up through the airlock, reach the open air, and then collapse. Their joints locked up with agonizing pain. Some went blind. Some became paralyzed. Some died. The workers had no idea what was happening to them. Neither did the doctors, at first. What they were experiencing is now called decompression sickness, or the bends. When you breathe air under high pressure, your body absorbs extra nitrogen. At normal surface pressure, the nitrogen stays harmlessly dissolved in your blood and tissues. But when you rise too quickly back to normal pressure, that nitrogen comes out of solution and forms bubbles, the same way carbon dioxide fizzes out of a soda bottle the moment you crack the cap. Those tiny nitrogen bubbles can lodge in your joints, your spinal cord, your brain. The pain is excruciating. In severe cases, it is fatal. The name the bends came from the workers themselves. When the pain hit their joints, they would double over and stoop forward. People on the street thought they looked like they were doing the Grecian bend, a fashionable posture popular among women at the time. The workers started calling it doing the bend, and eventually it became simply the bends. An alarmed Eads shortened his workers' shifts and brought his personal physician, Dr. Alphonse Jaminet, to the construction site. But Jaminet himself got the bends after inspecting the caissons, and the disease kept claiming victims. When the Eads Bridge finally opened on July 4, 1874, it had already cost several workers their lives to Caisson disease. To test the bridge before the public walked across it, Eads borrowed 14 locomotives from 7 different railroad companies and drove them back and forth across the span over the course of 5 hours. Together, those engines weighed around 550 tons. Thousands of people lined the St. Louis riverfront to watch. The bridge held. It did not flex. It did not groan. It held, and the crowd roared, and the fireworks went up over the Mississippi. Just a few years later, the Brooklyn Bridge adopted the same caisson technology on an even larger scale. The caissons for the Brooklyn Bridge measured 102 feet wide by 172 feet long. They were massive compressed air chambers, and the conditions inside were extreme. E.F. Farrington, the master mechanic on the project, compared the interior of the caissons to something out of Dante's Inferno, with strange noises and shadows and workers whose pulse rates sped up and slowed down for no apparent reason. 600 workers labored in those caissons, and by the time the project was over, the physician on site, Andrew Smith, had documented 119 cases of decompression sickness. 14 of those workers died. Smith became the first person to formally use the term Caisson disease. Some of the caisson workers wore bimetallic bands on their wrists, hoping the metal would somehow ward off the sickness. It did nothing. The chief engineer himself, Washington Roebling, developed severe neurological symptoms from the bends, including problems with his vision and difficulty walking. He ended up directing the rest of the Brooklyn Bridge construction from his sickbed in a Brooklyn Heights apartment, watching the progress through a telescope from his window while his wife Emily relayed his instructions to the crew. The cost of building in water was staggering, and not just in dollars. Every major bridge project of the late 19th century carried a body count. The men who drove piles and dug caissons were overwhelmingly immigrants and laborers with few other options, and the dangers they faced were barely understood, let alone mitigated. It would take decades before engineers developed safe decompression procedures, but the technology kept advancing because it had to. By 1901, the limitations of timber piles were becoming obvious. Wood was strong, but it was limited by tree size, vulnerable to marine borers and rot when exposed to air, and increasingly inadequate for the heavier loads that modern construction demanded. That year, a contractor named A. Raymond drove the first concrete piles for a building foundation in Chicago. Raymond went on to found the Raymond Concrete Pile Company, which became the largest pile driving organization in the world for most of the 20th century. Concrete piles could carry heavier loads than timber and could be cast in whatever length and diameter the project required. They did not rot, and they were not limited by the size of any tree. By the 1920s and early 30s, new railroad construction had slowed to a trickle, and the era of the railroad pile driver was fading. But the machines did not disappear. They evolved. Large crawler cranes and truck-mounted rigs replaced the rail-bound models, freeing pile drivers from the tracks and sending them to highway projects, building foundations, and harbor construction across the country. Around the same time, diesel engines began replacing steam as the power source for pile driving equipment. Diesel hammers worked on a principle similar to a car engine. Fuel was injected into a combustion chamber, mixed with compressed air, and ignited. The resulting explosion drove a piston downward with enormous force, delivering a blow to the pile head far more powerful than a steam-powered drop hammer. Diesel hammers were faster, more portable, and could deliver sustained impact energy for hours without rest. They became the standard for heavy construction by the middle of the 20th century. Then came vibratory drivers, which shook the pile into the ground instead of pounding it. The first vibratory pile driver was developed in the Soviet Union in the late 1940s, a model called the BT-5, and it could drive sheet piles 9 to 12 meters long in just 2 to 3 minutes each. The technology spread worldwide. By the 1960s and 70s, hydraulic systems were becoming dominant, offering finer control, less noise, and the ability to both drive and extract piles. That extraction capability was a big deal, because it meant contractors could recover expensive steel piles from temporary shoring after a project was done and reuse them. Today, pile driving looks nothing like what Otis Tufts saw at the Boston Custom House. Modern hydraulic hammers are mounted on crawler cranes and guided by GPS and laser alignment systems. Steel pipe piles are driven to depths of 100 feet or more to support skyscrapers in cities like New York, Chicago, and Shanghai, where the ground beneath the streets is soft, sandy, or sitting on top of old landfill. Highway bridges, port terminals, and retaining walls all depend on driven piles anchored to stable soil or bedrock far beneath the surface. But the most dramatic modern use of pile driving is happening offshore, in the ocean, where enormous steel monopiles are being hammered into the seabed to anchor wind turbines. These monopiles can reach diameters of 11 to 12 meters, roughly the width of a 4-lane road, and lengths of 60 to 120 meters. A single one of these piles can weigh over 2,000 tons. Specialized vessels called jack-up barges position themselves over the installation site, extend massive legs to the seabed for stability, and then use hydraulic impact hammers that deliver energy measured in thousands of kilojoules per blow. The noise from these installations travels for miles underwater, and environmental regulations now require bubble curtains and other acoustic mitigation to protect marine life during driving operations. The machines doing this work are the direct descendants of the drop hammers that the Romans used 2,000 years ago. The principle has not changed. You lift something heavy and you bring it down on top of the pile. What changed is the scale, the precision, and the power source. And somewhere beneath all of it, beneath every bridge pier and skyscraper foundation and wind turbine platform, there are piles. They are the part of the structure that nobody sees. The part that nobody thinks about when they drive across a bridge or look up at a city skyline. But without them, none of it stands. The Brooklyn Bridge, the Empire State Building, the offshore wind farms generating electricity off the coast of Europe and America right now, all of them depend on the same basic idea that ancient Scottish settlers figured out 5,000 years ago. You take a long pole, you sharpen one end, you stand it upright, and you drive it into the ground until it hits something solid. Then you build on top of it. That is what those Scottish settlers did on the shores of Loch Tay. That is what the Venetians did in their lagoon. That is what the men at the Boston Custom House were doing when Otis Tufts walked by and thought there had to be a better way. The materials have changed. The machines have changed. The scale has changed beyond anything those workers at the Boston Custom House could have imagined in 1840. But the principle remains the same. When the ground beneath your feet is not strong enough to hold what you want to build, you reach deeper. You hammer something solid down into the earth until it finds a layer that will not move. And then you build. If you found this one interesting, hit subscribe and leave a comment telling us what piece of hidden infrastructure you want to learn about next. Every like helps this video reach more people who appreciate how things actually get built.